Hello everyone, my name is Stéphane Côté. I am a research director in the Applied Research Group at Bentley Systems. During this presentation, I would like to describe our latest work in the field of augmented reality. Engineers and architects design infrastructures using models. Models are typically displayed and edited on a desktop computer. They are virtual and generally viewed outside of the real-world context. To help visualizing an infrastructure model in its real-world context, for instance before it is built, models are sometimes rendered in a more real context by adding textures, lighting, a backdrop image, or natural objects like trees. These techniques take objects from the real world into the computer. And one day we asked, what about doing the opposite? That is, taking the 3D model out of the computer and displaying it in the real world. Well, that's augmented reality. We started being interested in augmented reality 5 years ago, and we think it has a lot of potential in the infrastructure world. Here are a few examples. Let's say you have to periodically visit that building site. You want to check that the work progresses at the required speed and that the work is done according to specifications. You can take your drawings and compare their 2D contents with the building you're seeing. But checking whether there is a difference between the drawing and the actual building is, as such, a difficult task that requires attention to details. You have to guess what part of the drawing you're looking at on the actual building, abstract the fact that the building is not complete yet, extrapolate the third dimension from the drawing, etc. And if you want to make sure everything is at the right place, you will have to take actual measurements. The comparison would be much easier if you could actually superpose the model to reality. You could then display a wireframe version of the model for basic comparison, add more layers, see the model at a later completion date, and if your view of the site is not clear, you could also move around the building. The superposition of the model to reality could make your task easier. Let's say now you are interested in the underground piping network. You want to find the right manhole in order to check a specific pipe connection. For that, you can check your drawings, try to locate your own position within the drawing, and eventually find the connection you're looking for. That will tell you which manhole will give you access. An augmented reality system could let you find your pipe connection more quickly. The user would simply hold a tablet in his hands, and the device would display the network of pipes with interconnections to drains and manholes by superposing the pipe model to its view of reality. To the user, it would then become clear what is the connection between manholes. But in addition, the system could also display attributes on each element and show the way to the pipe connection that the user is looking for. Now, if you are a database user, you could also see references to your georeference documents in the real world. Finally, if you see something that should be fixed, you could put a sticky note with some explanation. The note, the virtual note, would be attached to the corresponding object in reality and could be seen later by a maintenance team who would also be using an augmented reality system. Augmented reality could also be developed as a tool for identification and query. For instance, an augmented reality system could let you highlight the position of a fire hydrant that would be hidden by a vehicle, like this. Or get information about a specific street drain by aiming at it with a crosshair and simply clicking on it. Similarly, users could view the IDs of real objects displayed in the real world. Augmented reality has a lot of potential in the infrastructure world. However, it is hard to achieve. Well, I will rephrase that. It is easy to achieve if you are ready to accept huge compromises. However, if you want high quality, engineering quality augmented reality, the task is a real challenge. Probably the main difficulty of augmented reality is registration. that is, the match between the 3D model and reality. In infrastructure engineering, a good registration is absolutely critical. For instance, a wrong registration like the offset shown here could lead to ambiguous interpretation and therefore bad decisions. A good registration is possible only if we know exactly the tablet's position and orientation. And a good registration is required because for engineering work, we cannot accept a 3D model floating in the air, loosely following the movements of the image on display. What we would expect from an engineering quality augmented reality system is perfect or near perfect match between the model and reality. Like this. You see the circle around the manhole. How can we achieve good registration of virtual elements and natural objects? Well, as mentioned before, the obvious way is by knowing exactly the orientation of the tablet and its position in real time. And if we don't measure the tablet's orientation appropriately, or its position, there would be an offset between the model and reality. Something that will look a bit like this. And the size of the offset will depend on how off we are from the true orientation. Let's say we need to develop an application that requires high engineering quality augmentation because we need to know the exact position of hidden infrastructure. So we will set our maximum error to 1 pixel on display. So the question is, what is the maximum error we can tolerate on the measurement of the tablet's position and orientation? We worked out that under those conditions, the maximum error we can tolerate for measuring orientation is 0.09 degree, and the maximum error for position is 3.6 millimeter. That is very small. And of course, we are expected to get that level of accuracy outdoor and in real time. That is not easy. Well, it could be easy if we were ready to install complex and expensive tracking devices around the user. But if we want minimum setup, anywhere augmentation, the problem is really not easy to solve. Well, one solution is to simplify it by adding constraints to it. As we saw in the previous slide, our calculations have shown that we need to measure the tablet's position with high accuracy. And the source of the problem is the user, who keeps moving. The solution to that is easy. We just have to ask the user not to move. But we figured that might not be a very popular solution. So perhaps we will let him use some equipment. What if we ask the user to put his tablet on a tripod? That definitely is a constraint, but that does have the advantage of offering a stable platform. Now, if you put a device equipped with a camera on top of a tripod, how do you think its camera sees the surrounding world? Well, it turns out that it would see the world as a panorama. Interesting. And so we came up with the idea of augmenting panoramas as a solution to the position tracking problem. A panorama is actually captured from a fixed position, so we don't need to track the user's position in real time. And we quickly jumped to the conclusion that we did not even have to make our own panoramas, but instead we could take advantage of those that already exist online. Think of Google Street View, for instance. So really the main problem we had to solve was how to synchronize a 3D model to a 360-degree panorama. So we worked on the problem and came up with a solution. In this example, you see a 3D model that has not been properly anchored to the panorama. And that is the result after anchoring. Okay, now that the model is initialized, augmentation is easy. Here is how it could work. Let's consider a situation where you're viewing a panorama and you see an object that you would like to identify. For instance, that manhole. So you aim at it with a crosshair on your tablet display and you click on it. What actually happens is the system finds the element of the 3D model that is closest to the location where you've clicked. The model is not visible, but since it was properly anchored to the panorama, each of its elements are at the right location with respect to their corresponding real-world object. Therefore, the system can display information about a real-world object simply by displaying the attributes of the corresponding model elements. That could be the ID, the maintenance history, basically any information related with that element that may be stored in the 3D model or in a database, etc. What you have then is a system that lets you query objects in the real world just by clicking on them. And for that to be possible, all we need is a 3D model that is properly anchored to the panorama. We have implemented that in our first prototype in the form of a desktop application. The user first loads the panorama, correspond to the area he wants to view, and then he turns on the layer of the underground pipes. That's actually a VGN model displayed in the panorama. And that model is actually alive. You can click on it and get information about each of its elements. That could be useful, for instance, for planning site visits. Now, since we are in a panorama context, we can move to another panorama and see another kind of infrastructure, for instance, that bridge that has not been built yet. And we can view it from a different position. So we thought that was nice. But what we really wanted was a tool for the mobile user. Okay, so let's say the user is on site. He wants to augment the scene. So we use the tablet's GPS to get its current location. The mobile device then broadcasts that current location to the panorama server. In return, the server would send the panorama that is closest to the current user location. Finally, the application tracks the instantaneous tablet orientation using its orientation sensor and displays the portion of the panorama that corresponds with that orientation. So what is displayed on screen is not reality. It is a panorama. But that panorama is displayed in the same orientation as the tablet, providing an illusion of augmented reality. So what we end up with is not an augmented reality application, but it is a very good approximation that has the advantage of offering an accurate and jitter-free augmentation. So here is a video of our mobile version. The user walks with his tablet on site with a preloaded panorama. And as the user moves the crosshair on the buildings, a 3D model appears that provides attributes to those elements. As the user turns around, the device displays the portion of the panorama that corresponds to his instantaneous orientation, letting the user augmenting other areas of his surrounding. He can view bridges before they're built, or viewing information about flushing sequence for hydrants. Basically, a system that lets you click on real-world objects to get information about them. Last summer, we pursued our exploration of panoramic images augmentation by studying another difficult problem, spatial perception. Augmented scenes often look supernatural. Adding 3D models to a real scene is unusual and sometimes confuses the brain that refuses to understand what it sees. That is illustrated here, where a 3D pipe model is used to augment a street scene. The photo is meant to show underground pipes through the ground. The augmentation is achieved by displaying the pipes on top of the image. If you had X-ray vision, that is possibly how you could see the pipes. The problem is that underground pipes are located under the road surface, so you're not supposed to be able to see them. Displaying the pipe this way creates a confusing image that is hard to understand for the brain. Such an image does not convey good spatial perception. It is too confusing to be useful. In our earlier prototype, we had also tried representing pipes with a wireframe structure, with perspective. Spatial perception is a bit better in this case, but the pipes still look as if they were on top of the road surface, not on the ground. The problem is that pipes are normally on the ground, so they should not be visible. If we want to augment a scene with hidden pipes, we have to find a way to make it clear in the augmentation that the pipes are actually on the ground. For that, we need an analogy with the real world. How do we normally see subsurface utilities? Well, we can only see them during installation or after excavation, and in both situations, we see them inside a hole. We are used to seeing that image. The brain is used to it and understands it. So let's do the same and display the pipe models inside a virtual excavation. That's what we've done in our latest prototype. That shows again a panoramic image. Now, in that panoramic image, we display a virtual excavation that shows inside 3D pipe model. The pipes appear to be inside a virtual excavation, making it more easy to understand for the brain. We've added tags to make sure we know what pipes we're looking at. And we can move that virtual excavation anywhere on the ground. Now we can also make that virtual excavation larger to let the user see more of those underground pipes and to get a good idea of what to expect for an excavation. Now we've also added the capacity for the system to display ground-penetrating radar scans. And when viewed in the context of a virtual excavation, the GPR scan is more easy to interpret, as we can more easily see whether the pipes in the 3D model were actually detected. That interpretation is possible because all those, that is, the GPR scan, the 3D model, and the surrounding buildings, are displayed together in the same context. In summary, we have developed 3 prototypes for panorama augmentation. One runs on a desktop and is aimed at seeing infrastructure in its real-world context from a remote location. It could be used, for instance, for preparing visits to the site from the comfort of your office. The second runs on a tablet and is aimed at being used on site for displaying information about real-world objects just by clicking on them. The last one is aimed at showing underground infrastructure in the real-world setting, that is, on the ground. Augmenting panoramas instead of reality has major advantages. It offers accurate augmentation because the user's location is calculated once and never changes. And the augmentation is also jitter-free because the user does not view reality but instead a panorama, and the model is anchored to it. Also, it lets the user augment reality from a remote location, which could be useful for areas that are not easy to access. However, augmenting reality through panoramas has disadvantages. First, it is not true augmented reality because we don't track the user's position, so the user cannot really walk in the scene. The user is constrained by the limited, discrete panorama locations. Also, the augmented scene is not real-time. Therefore, any real-time event like a vehicle or pedestrian will not be visible on the augmentation. Moreover, since the panorama has been captured some time before augmentation, the augmented scene may not be up to date with the real world. For instance, if a building was built after the capture of the last panorama, it will not appear on display. Finally, augmentation cannot easily be done from the same location where the panorama was captured, which would provide optimal viewing conditions. For instance, panoramas are often captured from the middle of the street, and we can hardly ask a user to go there to get good augmentation. Consequently, there may be a difference between what is displayed and what the user sees in reality. Our experience, though, shows that those disadvantages are minor compared with the stability and accuracy of the augmented solution provided by panoramas. Therefore, we believe that panorama-based augmented reality has a lot of potential, as it provides a way for users to augment the world now, without having to wait for position tracking technology to come up with more accurate and real-time solutions. That concludes my presentation. If you find our work interesting, don't hesitate to visit my blog on bee communities or to contact me. Thank you very much for listening.